In segment 3 of Twisting the Dragon's Tail, the narrator introduces us to the idea of half-life. Half-life, given the symbol T1 half, is the amount of time it takes for one half of the radioactive nuclides in a sample to undergo radioactive decay. We looked at cesium, which had a half-life of right around 30 years, compared to uranium, which has a half-life of millions and millions of years, and the narrator talked about some of the dangers of these things. Today, I've put together a video that uses some props from around my house to help you begin to understand the idea of half-life. In the first simulation, we're going to simulate radioactive decay that has a stable daughter nuclide. The radioactive isotope in question here is an imaginary radioactive isotope called dadium, shown right here. Dadium undergoes alpha decay with a half-life of 30 seconds. It gives off its alpha particles and creates blankogen. Blankogen is a stable nuclide. We call that, as you'll remember, the daughter of dadium. I would like you to watch this little simulation and fill out a chart that looks like this. You'll be able to see the dadium laying on the table, the blankogen that's created, the emitted alpha particles, and there will also be a timer there for you to watch. You can pause the timer every 30 seconds and figure out how many of these emitted particles you have and how many blankogen and dadium nuclides you have at that point in time. You're going to populate this chart at 30 seconds, 60 seconds, 90 seconds, and 120 seconds as the simulation runs for 2 minutes. Simulation 2 represents a slightly more complex situation. When a radioactive nuclide undergoes radioactive decay, there's no guarantee that the daughter nuclide is going to be something that doesn't itself undergo radioactive decay. So in the next simulation, dadium undergoes radioactivity to make blankogen, but blankogen itself is a radioactive isotope, which will undergo radioactive decay to form a new nuclide called edgmium. Dadium is an alpha emitter, blankogen is a beta emitter, and as would usually be the case, the mother and the daughter nuclides don't have the same half-life. We'll maintain a half-life of 30 seconds for dadium and go with a half-life of 45 seconds for the resulting blankogen. This simulation is a slight oversimplification of the situation because in actual radioactive decay, the blankogens would begin undergoing radioactive decay as soon as they were formed. In this simulation, we wait until 30 seconds before we start having the blankogen undergo radioactive decay. So in the next simulation, because of the complexity of this, I'm going to have you count what you have in the beginning and then what you have in the end, and not try to track what actually goes on in between. I hope you enjoy the cameo appearance of Taz's head midway through the video. For the last part of this activity, you're going to answer some follow-up questions. Follow-up questions will be on screen, or if you printed the handout that goes with this, you can answer them right on there. Answer the questions as they appear on the screen, writing your answers either on your printed sheets or on a separate sheet of paper. Pause the video to give yourself enough time to answer the questions before the video moves on to the next set. For question 7, you're going to create a half-life T-chart. A half-life T-chart lists the amount of time that's gone by, coming down the left side, and the amount of radioactive isotope remaining, coming down the right side. I've populated the first 2 rows for you to get you headed in the right direction.